So in this lesson, we're going to look at two new rules for how to take derivatives, and I call these structural rules. They're not rules on how to take the derivative of particular functions. They are rules about how to handle different ways that function.
Is what's known as the product rule. And it's a rule that shows us how to find the derivative of two functions that have been multiplied together. Remember that if we have to take a derivative, we learned last time that derivatives go term by term. So if I have a three-term polynomial, for example, like this, I just can take the derivative of this, and I can take the derivative of this, and I can take the derivative of that. I would get, 3 times 7, 21 x squared minus 2 times 5, 10 x. Remember, the power drops by 1 each time. And the derivative of a constant all by itself, a constant term, the derivative is 0, so plus 0, which I won't write. So we know that derivatives go term by term in a very straightforward fashion. However, what's not the case is if we multiply functions, things are not quite so easy. So for example, if I had 4x squared minus 7x plus 3 times 8x to the 5th minus the square root of x, and I needed to take that derivative. This is a product. We have this function times this function, and unfortunately you can't do what you did with products, like what you did with the individual terms here. You can't just say, well, I'm just going to take the derivative of this and multiply it by the derivative of this. That's just not the way the world works. So we have to learn a new rule here on how to handle when we multiply two functions together, and that rule is called the product rule. And this is the first of three really important rules that deal with how functions are combined and put together to make new functions. This is the first one, the quotient rule, and then the very important chain rule, which we'll deal with in a future lesson. So let me give you the idea behind how we're going to figure this out. So let's say we have some function or some expression, we'll say it a, which is a function of x. And we know that it goes like this. We've learned how to understand the derivative. And if I look really closely here, get it infinitesimally close, this will look like a straight line. And what I'm interested in doing, and what I'm interested in understanding here, is what happens if I'm at some point A here, and then I change. This is the point. Actually, no, that's not A. Yeah, I have some particular x, A, and then I'm going to move over a little bit, and this will be, x plus dx, A plus d. Here is my change in x. And this in here is my change in A, and I have this ratio dA dx, this infinitesimal slope, which is the derivative. Just want to get this idea that I'm interested in looking at understanding that dA represents a very, very small change in A, and dx represents a very, very small change in x, and dA dx is going to be the derivative. So what I want to do now is I want to change. I'm going to take two quantities, A and B, A and B. I'm going to multiply them together. So I get A times B. And I want to look back up here and say, I'm going to change A by a little bit, and I'm also going to change B by a little bit. If I change A to A plus dA, so I increase A by an infinitesimal little amount, like we did right here. A
went up to A plus dA. And I change B to B plus dB. How much does A times B change? This is going to give us the basis for our product rule. I'm going to change A to A plus dA. I'm going to change B to B plus dB. And I want to say, okay, well, how does that affect the product? How does that affect A times B? And I'm going to do it in as straightforward fashion as possible. I'm going to simply take this and I'm going to change A to A plus dA. I'm going to change B to B plus dB. So now I've changed A by a tiny little bit. I've increased it by dA. And I've changed B by a tiny little bit. I've increased it by dB. And I want to try to figure out how does this affect A times B? What's the change in AB? So I have this product. This is just an ordinary multiplication of two polynomials. So I'm going to distribute this out. I'm going to FOIL this out.
Plus dB times A plus dA times B plus dA dB.
Now if I look at this expression over here, I get this big mess. AB, A times dB, B times dA. Then I have dA times dA. This is a product of two infinitesimals. So this is really, really vanishingly tiny. It's like an extra order of infinitely small than these. Now, of course, this is a real number. This is A times B, and this drowns all this out. But what I'm interested in is how does A, B change. So this is my original AB. So here's AB, and this over here then is the change from AB. This is what I started with. I started with A times B, and so what's happened is when I've gone to A plus dA and B plus dB, I still have AB, and then here's the change. And what we realize here is that this is an order of infinitely smaller order than either of these, because this is just dB times a real number. This is dA times a real number. This is two infinitesimals multiplied together. So this is so tiny that this doesn't matter. This is essentially 0. It disappears. And I know there's a little bit of hand waving on why this works, but it gives the right answer. You'll have to trust me on this, and we're going to do the more rigorous version of this later in the year. So what I get is that this expression right here gives the change from AB, and this expression is called the product rule. I'll write it like this. When I want to take the derivative of A times B, the change in AB is given by this expression. And I'm going to rearrange this. I'm going to write it as dA times B plus dB times A. This is the product rule. Let me show you how this works in practice. I'll have to recopy it. So, how does this work in practice? Well, the way you understand this, the way to read this is you say, if I want to take the derivative of the product of two things, I've got A times B, then what I do is I take the derivative of A, and then I just multiply it by B, no derivative. Just do derivative of A times B. And then I get a second term, which is the derivative of B times A. So notice that there's only one term here. This is just A times B, but when you use the product rule, it produces two terms. You get dA times B plus dB times A. Let me give you a couple of examples of this, how this works. So first of all, let's do one that we wouldn't have to use the product rule on so that we can check that we understand what's going on. Let's say I want to take the derivative with respect to x of x times 4x squared plus 3. So I want to take the derivative, x times 4x squared plus 3. Now, of course, we don't have to use the product rule here because we could simply multiply this out. So what would we get if we did that? So if I were to distribute this out before taking the derivative, I would get 4x cubed plus 3x. And now I would have an expression where I don't have to use the product rule. I can simply do the derivative. Using the previous rules we have, we've got two terms here. The derivative of 4x cubed, the 3 comes down, and I get 12 times x squared. And then the derivative of 3 times x is just 3. The derivative of a number times x is always just the number. So we know this is what we should get for the answer. Now let's come back up here and use our new rule to verify that it is giving the same answer as this. So when I'm using the product rule, I'm going to think of this as being my A, and I'm going to think of this as being my B. So according to the product rule, I want to do the derivative of A. So I'm going to do dx times, and then I just leave B alone, and I don't take its derivative, plus, then I'm going to take the derivative of B, so I have d 4x squared plus 3 dx, and then I have times A just left alone, times x. And this is a feature of product, quotient, chain rules, these rules that deal with putting functions together rather than just rules for taking derivatives of new functions. I can't read that 3 very well. The feature is that what I've done here in applying the product rule is I still have derivatives to take over here. The problem's not finished. I've replaced this with a new set of problems where I have to still take derivatives. This is going to be a feature of the product rule, the quotient rule, the chain rule. You see over and over again these transformation rules where you say, I need to take the derivative of something that's a product. I apply the product rule and I'm still not done. I still have derivatives that I need to take. Now here we know how to take these. Dx is of course 1. We get 1 times 4x squared plus 3 plus, and then I have the derivative of 4x squared plus 3, so the 2 comes down and I get 8x. And then the derivative of the constant term 3 is just 0. And there's my answer. Is that actually the same as this? Well, you can see that it is. I've got 4x squared plus 3, and this is 8x squared, so I have 4x squared plus 8x squared, that's 12x squared, and there's my plus 3 plus 3. So this does at least verify that we're doing things correctly. If I use the product rule and then I use the other method for taking derivatives, we get the same answer. So how about one where the product rule actually helps us, where we have something where we would not be able to or not want to do it without the product rule. For example, let's say I have some function of, let's use a different variable. Let's say we're going to do z. And I have 3z to the 4th minus 7z plus 8 times 15 cube root z minus 3 over z to the 4th. Yuck. That's a bit of a mess. Now I could avoid using the product rule again. I could say multiply these 3 terms by these 2 terms, multiply everything out, and just do it term by term. But that would be a big mess. I'd have to distribute each of these terms onto that, distribute each of these terms onto that. I'd have all these fractional. It would be clearly a mess. So we're going to use the product rule. The first thing we're going to do is we're going to note that for taking derivatives, I would much rather write this term right here as 15 z to the 1/3, and I would much rather write this term as 3z to the -4. So I'm going to take the derivative this way. What I'm going to do for my product rule is I'm going to view this first factor as my a, this second factor as my b, and I'm going to apply the product rule. So the product rule tells me I take the derivative of a. I'm being very careful here because we're learning how to do this to write out exactly what's going on for clarity. You might be able to do some of these steps, like you might be able to just take this derivative in your head rather than writing it out. Anyhow, so I take the derivative of a, and then I just recopy b. Derivative of a, I can't see that. Derivative of a times b is the first part. Then plus, I'll have the derivative of b times a. So the derivative of b would be d dz 15 z to the 1/3 minus 3z to the -4. Then I would multiply by a. 3z to the 4th z plus 8. I'm not done yet because I still have a derivative to take here, and I still have a derivative to take here. These are just going to recopy. So when I take this derivative, I get 4 times 3, 12 z cubed minus 7. Derivative of 7 times z is just 7. The derivative of 8 is 0, so that constant term disappears. And then I have to recopy this bit. Plus, and then over here, I have to take the derivative of this expression. So the 1/3 comes down, multiplies to 15, and I get 5 z 1/3 minus 1, negative 2/3. And then I get negative 4 coming down times negative 3, which gives me plus 12 z. And then I have to subtract 1 from negative 4, which makes it a bigger negative number. I get negative 5. And then this recopies. Is it a mess? Yeah. Oops. It is ugly. But it's what you have to do. It gives the correct derivative. So that's how the product rule works. The other rule we want to look at today is the quotient rules. Let's have a look at that now. You can guess what the quotient rule is about from the name. Product rule is about multiplying. The quotient rule is about dividing. Now we're going to generate the quotient rule in the same way that we generated the product rule. Okay, I'm going to have a and b, but now we're going to divide them. I'm going to ask the question, how does a over b change if I add dA to a and dB to b? So I'm going to increase a by an infinitesimally small amount. I'm going to increase b by an infinitesimally small amount. I'm going to say, how does this change a over b? So let's do it. Here we go. I've added a tiny little amount to A, and I've added a tiny little amount to B, and I want to do some clever algebra to try to figure out what happened to, how does A over B change? And the clever algebra I'm going to do, and you wouldn't know to do this unless someone told you, and that's someone told me at one point, is I'm going to multiply top and bottom by B minus dB. This forms the difference of squares multiplication pattern on the bottom. And we're going to exploit that here in a second. So I'm going to multiply the top and bottom by B minus dB. So I need to distribute this out. I need to distribute this out. When I distribute them out, I get AB excuse me, minus, let's do plus dA times B minus dB times A minus dA dB. This looks a little bit like the product rule, except for the minuses. But you've got this bottom of the fraction. How do I deal with that? Well, like I mentioned before, this is the difference of squares factoring pattern. So I'm just going to get B squared. This inner and outer terms in the FOIL subtract each other away, and then I have minus dB times dB squared. Now it's a big mess, so you have to figure out what to do with this. First, we're going to make several observations. The first is we have these second order differentials again. We have this dA times dB, which is vanishingly tiny, and we have this dB times dB, which is vanishingly tiny. So we're going to say these are basically negligible. They're so tiny that they're not going to affect our answer. And then we're going to look at what we have left. We have AB plus dA times B minus dB times A over B squared. And I'm going to make an observation. I'm going to look at this first part here. If I pull this first term out of this fraction, I get AB over B squared. Then I'll have the rest. And what I want to observe is AB over B squared is just A over B. And remember, we're looking in how does A over B change. So there's A over B again. So I've made this alteration to A over B, and I'm going to see I've got A over B plus a change in A over B. And that change in A over B is going to be my quotient rule. And what is the quotient rule? Well, the quotient rule is what's left over here. So if I just rewrite this, I get dA times B minus dB times A over B squared. And I'll just recopy it again here for completeness sake. So we ask the question, how does A over B change? If I replace A with A plus dA and B plus dB, and I have, well, here it is, it's A over B, that's what I started with, plus the change. And this change right here is the quotient rule. And it's quite messy. So the quotient rule is the derivative of A over B is this. So we take the derivative of the top first, multiply by the bottom, minus, then we take the derivative of the bottom, multiply by the top, and then we have bottom squared, no derivative, just the original bottom, and we square it. It's a mess, and we avoid using it when we can, but there's many circumstances where it's either unavoidable or the alternatives are gruesome. So let me show you just one straightforward example of how to use the quotient rule, and then we'll be done. So here's my example. My example is, can't see it, there we go, is let's say I want to take the derivative with respect to, oh, let's do a new variable. Let's use a theta. How exciting. Of 3 theta plus 4 over theta squared plus 2. So here we have a quotient. So let's look at our quotient rule. There's the quotient rule. So I want to apply this transformation rule to this derivative. So the a is the top of the fraction, b is the bottom of the fraction. So when I look at my fraction here, this is going to be playing the role of a, this is going to be playing the role of b. So now, unlike the product rule, the quotient rule has this minus, which means you have to make sure you take the derivative, you do the correct term first. If you switch them around, then you'll get the negative of the correct answer. But just remember top first. The derivative of the top is what goes first. Boom. You're going to start off with derivative of the top. So I have derivative of a times b. So I'm going to have derivative of the top, 3 theta plus 4, and I'm going to have times theta squared plus 2 minus. Next, I have the derivative of the bottom times the top. This minus is going to end up being annoying because it's going to have to distribute onto everything that you get from this mess in the second part, so you just have to be careful with it. Anyhow, derivative of b, derivative of the bottom next, theta,
and then big fraction bar, and then I just have b squared. So I'm going to take the bottom, and I'm going to just say I want to square that.
Now we're done with the quotient rule. We've applied that transformation rule. Now we just have to deal with these little derivatives that we've created inside here. Then we'll be done. And these little derivatives are straightforward. The derivative of 3 times my variable, I'm taking derivative with respect to theta. The derivative of 3 times my variable is just 3. The derivative of the constant by itself is 0, so I'm going to get 3. And then I have a recopy. Minus. Here's my next derivative, theta squared plus 2. So this is like x squared, so my variable is theta. So I just get 2 theta. The derivative of a constant by itself is 0. Over theta squared plus 2 squared. And there we have it. If you're just practicing taking derivatives, you could just stop there and say, okay, that's it. I've been practicing the quotient rule. All my derivatives are done. I'm finished. You would never want to multiply out the bottom. However, there may be the derivative bottoms of fractions are always better factored rather than multiplied out. But there may be circumstances where distributing out the top and simplifying theta squared
plus 6, distributing in the 3, and then I'm going to distribute minus 2 theta onto that. So I'll get minus 6 theta squared, and then minus 8 theta over theta squared plus 2 squared, and then I can collect together like terms, and I've got those like terms. So I get minus 3 theta squared minus 8 theta plus 6 all over theta squared plus 2 squared. And if you needed this might be easier if you're plugging numbers into than that. And that is the quotient rule.